we have looked at magnetism a few different ways, and now there's something else we need to add. Now, magnetism does something that electricity just doesn't, and it's odd. It's really strange to wrap your head around. I want to get started with it, and the thing that we need to be able to get started with it is the idea of magnetic flux. Now, we can talk about electric flux, but there is one major application of electric flux, and it more or less requires calculus. There are some very specialized cases you can do otherwise of electric flux, called Gauss's law. But if we're not doing that, and that's not part of this course, then this is probably the first time that we've come across flux at all. So flux gets a symbol of an uppercase Greek letter phi, because why not? And if we're talking magnetic flux, we usually do phi sub b. It has units of Tesla meters squared. And I want to give you kind of an idea of what this looks like. So flux is a measure of how much magnetic field is passing through a closed loop. If I've got a loop like this, and I've got a magnetic field, then flux is a way of finding just how much magnetic field passes through my loop. So I'm going to take right here, this area, and this area is exposed to a magnetic field. Some of the magnetic field passes through, some of it will be tangent to that, and flux is going to be somehow or other a quantitative measure of this. Now, the way that I like to think of this is if I have a bucket like this, if I have a bucket like this and it is raining, I will make the rain blue because red rain looks really foreboding. Magnetic flux, or rain flux, I guess, would be kind of a measure of how much rain is getting into my bucket. So that's going to depend on a couple of parameters. One, it's going to depend on how hard it's raining. And we'll translate all these back to magnetism in a moment. Two, it's going to depend on how big is the bucket. And three, it's going to depend on how we're oriented. If I take this bucket and I rotate it, I could catch more rainwater. If I rotate it the other way, like this way, I might catch less rainwater. So somehow or other, the orientation. So now we want to turn these into magnetic quantities. How hard it's raining? That one's easy. That is the strength of our B field. How big is the bucket? That sounds like an area. So that is this area right here. The orientation sounds like an angle issue. So over here I'm going to say this is a B field times an area already, but the orientation is an angle issue. If I want to catch more, I would like the bucket to kind of be rotated up this way, so it's hard to quantify that maybe. And the way that we do this is to say here is a normal vector. If you remember the normal vector from way back during optics, it's just perpendicular to a surface. In this case, it's perpendicular to the area, perpendicular to the plane that contains the area. What I would like is to express this in terms of an angle between that normal vector and the magnetic field. And what I can see right away is that when that angle is small, when that angle is 0, my bucket is facing straight up and down. I would like 0 to be the angle that gives me the most flux, and I would like 90 degrees to be the angle that gives me the least. So that sounds like a cosine function. And that's really it. That's my magnetic flux. When I'm back here, it is, again, this measure of how much of the red magnetic field is passing through my loop versus the blue rain, but there's not really any big difference there. If I have, because these are the sorts of questions that come up with this a lot, maybe I have a region like this, and I have a magnetic field that points into the screen in this region. And I have a loop of wire like this. That wire, this part of my wire, is exposed to the magnetic field, and this part up here is not. So my flux in this case, and I would probably need some dimensions. If this is the whole height of the wire, and this is the whole width of the wire, and maybe this part can be y, then my flux is going to be the B field strength times the part that's exposed, so y times the width, just the yellow part, and then I need times the cosine of the angle between them. In this case, my loop is laying flat on the screen, and my magnetic field is pointing straight into the screen, so all my field is passing directly through here. So I'm going to say this is a cosine of 0 degrees, or I'm just going to ignore the cosine part and say it equals 1. That's how I'm finding flux. That's really the whole process.